Welcome to Kashupi and Johannes. I hope you are doing well.
Good morning, sir. Yes, I'm doing well.
Great. Okay, so without any further ado, let us dive straight into what we tackled yesterday. In fact, we started the introduction of the QR decomposition method, but we didn't go that far. And I asked you to read the note so as to prepare, so that I can address the main important aspect of the method. So for the QR decomposition, as I said, it's similar to LU decomposition. For the LU decomposition, you have L, which is a lower triangular matrix, and U, which is an upper triangular matrix. But in the case of QR, L is replaced by an orthogonal matrix, the way I explained yesterday, and U is still upper triangular. That's the difference. Okay, so, and the advantage of orthogonal matrices is that you don't need to invert the matrix. If you compute the transpose, which is the easiest thing you can do, the transpose of the matrix is its inverse. You see, that's the beauty of working with orthogonal matrices. If you transpose, it's equal to its inverse. That is it. That's one of the advantages. So let's go straight to the note. Okay, so this is where we stopped last time. Now, let us see the application of that QR, this decomposition of matrix, this QR decomposition. How can that be useful in real life application? Before we dive into how to compute a QR decomposition of a matrix, let's see how it is used, right? Okay, now assume that we have this matrix A, which is a symmetric tridiagonal matrix. You can see we have 3 diagonal here, and it's symmetric. Symmetry means that if I compute a transpose, it's exactly the same. And you can see this B2 is the same here, this B3 is the same here, and so forth, Bn, Bn. So if it's transpose, it's still the same. Okay. Now, if we have a symmetric tridiagonal matrix and we perform the QR decomposition, we end up with a diagonal matrix. Roughly, that's the idea. But what if the matrix is not like this? If the matrix is not tridiagonal, what we will do, we will first perform what we call the house order method. Of course, to a symmetric matrix, in order to convert it into a tridiagonal like this. And once we obtain the tridiagonal matrix, we can apply the QR, right? So that's what we have here. That QR algorithm is applicable to a symmetric and tridiagonal matrix. Because if you have symmetric tridiagonal and we perform the QR, remember that the purpose is to get what? Eigenvalues and eigenvectors. That's the purpose. Because we need the eigenvalue. So if you have something already in this form, you perform your QR, you obtain the diagonal matrix. If you have the diagonal, it means that you have the eigenvalues. That's what the diagonal matrix gives you, the eigenvalues of the original matrix. Okay, now if I'm given a matrix, a symmetric matrix, of course, you have to be a symmetric matrix. And now, I want to find its eigenvalues. If the symmetric matrix that I have is not tridiagonal, the first thing I have to do is to perform the house order method to that matrix to transform it into a tridiagonal matrix before I can perform the QR. So those are the steps. Right. Okay. Now here you have the description of how that works. But look at this theorem. If you use this theorem, which you know from linear algebra, you know that from linear algebra. If A is a symmetric matrix and D a diagonal matrix, then we can find an orthogonal matrix Q such that the diagonal matrix can be written as Q transpose AQ. Yeah, so in linear algebra, this is what we stop here in linear algebra. We did not use the transpose. Just stop here. Okay, now if you use your MATLAB, if you use your MATLAB function QR, you take A and you call QRA, and then you write this to the left-hand side, Q and R. It will give you the Q and the R. So if you do that using your MATLAB, this is what you will get. Your Q will be this, and your R will be that. And you can see that your R here is an upper triangular matrix. You can see it from this structure. And you can check to see that if you multiply your Q by I, it returns the original matrix A. This one. And that is exactly what you have here. But you will not waste time on that. You can read your note and perform all these operations yourself. But what we are going to do next is the QR factorization using Gram-Schmidt's process. Right, so we are going to do that together step by step, because I remember that I made a correction on this, but I don't remember, because this one, I did not update it on the new document, because I'm still using an old document. That's why I myself, when I look at it, I don't, okay, I think it should be this, it should be exactly that. But let's do that together. Let's do that together so that at least you'll be learning at the same time. So we are going to apply the Gram-Schmidt's process to this matrix A to obtain the QR factorization. So what I would do, I will write this down on a piece of paper, and then I will open a new slide, and we are going to perform the QR factorization together. So the original matrix A, the components are, the first column is 1, 1, 1, then 1, 4, 1, and finally 4, 2, 0. And okay, so let me open the new slide, and we are going to do that together. Right. So you already have this, you can read it, but let's perform the computation together. So here we are talking about QR factorization. Okay, so what is the Gram-Schmidt process? In linear algebra, the Gram-Schmidt process is when you have a basis, right? You have let's say, for instance, you have a system, a basis in general. That is, the vectors are linearly independent. So you have this basis of V1, V2, V3. We can stop here for R3, vectors of R3. Linearly independent, right? In R3, if there are three linearly independent vectors in R3, they form a basis of R3. Now, Gram-Schmidt process will transform this into an orthonormal basis. So, Gram-Schmidt process, I will call this GSP, Gram-Schmidt process. So, if I perform the Gram-Schmidt process to this, I obtain a new basis. Let me call it that F U1 U2 U3, and this now will be an orthogonal normal basis of R3. So this is what Gram-Schmidt process does. To be orthonormal, what does that mean? It means that for any I, J, if I take U sub I dot product with U sub J, this gives me delta Ij. And you know this is the chronicle delta symbol, meaning that if I is equal to J, this is identity. And 0 if I is not J. So meaning that two different vectors, their dot product with 0, so they are orthogonal. Normal meaning that if I compute U1 dot product with U1, it will be 1, meaning that the norm of each one is 1. So they are unit vectors. We call it also unit vector. So each element here is a unit vector, and the dot product of two different vectors will give me 0. So that's what I call orthonormal basis. So, okay, and now how do you perform this Gram-Schmidt process? So once you understand this, you are done. So in order to perform the Gram-Schmidt process, we would, the first U1, we take U1 to be V1. That's the first step. You don't change. Your V1 is fixed in the new one. It's just V1. Now for U2, what you do for U2, what you will do with U2, you will take V2. V2, because remember, you want to construct U2 in such a way that U2 and U1 are orthogonal. Orthogonal means that the dot product is 0. Right. That's the idea. So meaning that you construct U2 using V1. Because V1 is related to U1. So you take U1 and you knock out everything that will make it, you knock out the component of U1 in such a way that U1 and U2 will be orthogonal. Right. So I take U1, which is V1, unchanged. Now to construct V2, or to construct U2, which I assume to be orthogonal to U1. So for that to be true, I will construct U2 from U1 by knocking out all the components in U1 in such a way that the two become orthogonal. Now, how do I do that? It's by the projection. So I will project V1 or U1 along I will project U, V1, V2. Okay, I will take V2, and then I will project it along U1, and I will subtract it from V2. And then the result will be obtained. So let's do that and test and see if it will work. So I use this one, U1, which is V1. So this is U2, sorry, V2, this is V2. I take V2. Well, this V2 is, yeah, it's the current one, because I already used V1, which is this one, which is U1, right? Then I move to the next one, which is V2. I move to the next one, V2. I take that V2 and I subtract the component. So I will project that V2 onto what? Onto U1 or V1. Yeah. Do you see this? Do you also see this line?
Yes, sir.
Anyway, I don't know how it appears. I tried to erase it, but it is not. It is not erasing. But however, we will just proceed. Okay. So we project that on U1. Right. So you see that, okay, so this is the next vector that we are using, this one, V2. You see that for U1, we took V1. Now for U2, we also take V2, but we subtract its component on U1 in such a way that if I now take this V2, this U2 and U1, they will become orthogonal. So this is how I do that. I subtract that component from the projection of V2 on U1. If I do that, then the two become orthogonal. Now, how do I check that the two are orthogonal? It's just by performing the dot product. If I perform the dot product, this will give us 0. But let's compute. Let's compute that. And what is the projection? We will see what the projection is. So this is V. Okay. Let me write the algorithm. We don't have any matrix here to perform the computation. Let us just, I'll write the algorithm. I will do for the U2 also. So U and the last one. So now for U3, so you can imagine U3 now we take V3, right? Because remember, I want to match V1 to this, V2 to that, V3 to that, right? So for V3, for U3, we use V3, right? V3. And now from V3, I subtract all the components of the projection on U1 and U2 because I want this U3 to be orthogonal to these two vectors, U1 and U2. So I'll do exactly what I did here. So I will project V2 or V3 now on U1, and I'll also subtract the projection of V3 to U2. U2. So that is it. So that is the Gram-Schmidt process. Okay, at this stage, they are just orthogonal. They are not yet normal. Right. So once I compute all that to make each one of the vector normal, so I can call this U1 prime first because it is not yet normal. I can call that prime, 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 prime. Now I just use this UI will be equal to UI prime by its norm. So that would be my UI. for I equal to 1, 2, 3. So I first compute this and then I normalize them by dividing each one of them by the norm. And that's what I will call U. So that's the Gram-Schmidt process. Gram-Schmidt process. That's exactly this. This is the process. Now we are going to apply this to our matrix application. So we are going to apply this to our matrix. All right. Now our matrix A is one, 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 and then 1, 4, 1. And finally here, 4, 2, 0. Now, remember that this column is a vector. This column is a vector, this column is a vector, so I can write this as the matrix with this first column, I'll call it x1, second one, x2, and the last one, x3. Now you see, when we are writing it like this, we have a basis in R3. Yeah? It's similar to this one. Obviously, it's no longer called V1, V2. Okay, I can still call it U1, V1, V2, V3. Eh? It doesn't matter. So it's just a notation. So let me change that. So to keep, so that is V2, V3. Right? You can see. So we are back to that, and then we apply. So let us quickly apply. So we want to convert this into, okay, what we call F. U1, U2, U3, which is an orthonormal basis. So U1 prime is equal to V1. And what is our V1? I will just write it like this. Right, to save space, I will use the transpose. So that's our V1. U1 prime is this. Right. Now, what is our U2 prime? It will be V2 minus, we subtract the projection of this V2 on U1 prime. So what is this? So V2 is 1, 4, 1, 1, 4, 1, minus, now for the projection, I will take the dot product of these two, right? And I divide by the norm of this. So what, let me write the formula here. So this is the dot product U1 prime with V2, right? Because I project, I project along this, meaning that I project it on the line, or the on the line carried by the vector u1 prime, right? This one carried by this. So that is, I will multiply that by u1 prime, u1 prime, like this. Is that okay? Because I project along that. I project along the line that is carried by that vector. So I will divide. I project, but because it's carried by that, I divide by like the norm square. Because u1 prime into u1 prime is like it's norm square, right? Okay, so that's what I do. So what is that? So this is equal to, obviously after that, of course, it is carried by this. So meaning that I will, since it's carried by that, this is just a number. This is a number. That is the projection. So all this is the projection. This is the projection. But I say that it's carried by what? If it is carried by a line, it means that it has to be linear to that vector, right? So linear to which vector? This one, u1 prime, because it is carried by u1 prime. Is that okay? Is that okay? Are we together? Hmm? Look, geometry, a bit of geometry. A bit of geometry. Let's say this is, we are here.
Yes.
Right. Let's say that this is a line. And this line is carried by a certain vector. Let's say that this vector is u. Of course, in geometry, you put an arrow there to indicate that it's a vector, right? But like this. Now, if I have another vector here, let's say that this vector is v. And I want to project this vector v here. What will happen is I will project this on this line. Now, it depends which type of projection now I will perform. Is it orthogonal projection? If it's an orthogonal projection, I will make sure that the two lines are, in fact, I will make sure that I project it this way. Okay. I'll do something like this. I will take this also orthogonal like that. And now the projection of V on that will be here. Let me use, let's say the yellow. Let's see if the yellow will work. Oh, I don't even see. Yeah. Ooh, don't even see properly. Oh, the yellow is not good. Oh, maybe the green. Okay, let me try with the green. Yeah, I want it to be thick so that you can all see. Yeah, it will be something like this. Orthogonal projection will give us something like this. Now, you can see that this new vector, if I call it V prime, the projection, is carried by this line. You know that collinear, in geometry you say they are collinear. So if two vectors are collinear, it means that I can write V prime as alpha u, because I'm projecting this V prime here. So you see that it's carried by this line, so meaning that it will be this alpha into u, because u is the vector that gives us the direction of let's call this line delta. I project it along delta, right? And the direction of delta is given by this unit vector. I mean vector, but we make it unit vector, right? You usually make it to be a unit vector. So that's how you take it. Now this alpha is that projection that we are talking about. So the alpha is the projection that we are talking about. It's the projection of what? Of V along U, like this. And that it will be the dot product of the two into, because I projected along U, so that will be norm of U squared, which is the dot product of U by dot product of U. So that's how you compute that. Okay, so that's a bit of a recall geometry, so for you to understand. Okay, now I'll continue with the computations. I hope this is not a waste of time, what I've just done. And that's just a bit of geometry. So this is a recall. About geometry. Okay, now back to what we were doing. Now, what is this? What is that projection? So we have 1, 4, 1. Now, U prime V. This is U prime times V2. What is V2? V2 is this one. So that will give us 6, right? Because V times 1 plus this times 1 times this plus 1, that will be 4 plus 2, 6. So this will be minus 6 into, now if I take this one, it will be 3, right? Norm square with this plus this, that will be 3, right? So finally, this is 2 into 1 prime, which is 1, 1, 1, 1, 1, 1, right? And the final result, remember that this is 2. Huh? So I will subtract 2 to each of these components. So this will be negative 1. This will be 2. This will be negative 1. Right. So this is our U 2 prime. And I hope that's what we have on the slide. 1. What is it? I don't really know why here we have 5. What do we have 5 there? 5 by 2. Is it 5 by 2? I don't think so. Anyway. Okay, so we wrote everything here is fine. Eh? We have 1, 2, 3, and then that. Okay, so u1 prime into that. Okay, so this is what we get, né? We all agree, yeah? Are we together? This is 6 by 3, right? Okay, now we proceed. We proceed with the next one. So I will write, okay, so I can copy. Okay, so let me copy this. And then paste it here. So what is this? V2. Oh no, we are dealing now with U3, eh? Not this one. Oh, sorry. So what is this? Actually, it's this last one. Okay, so what is it? This is V3 is 4, 2, 0. Am I right? That's our V3 minus. Now we take this projection. Let me write the projection. So this will be U1 prime into V3 U1 prime, U1 prime, and then it's carried by U1 prime minus the next projection, which is U2 prime dot product with V3 by U2 prime, U2 prime carried by U2 prime, right? Here we U1 prime. Okay. So what we know already what is our U1 prime and U2 prime. So we are going to substitute all that. So so this is equal 4 to 0 like this minus So U1 prime times V3. U1 prime is V1, right? U1 prime is V1, 111. So it will be 6 again. You can see, if I multiply this by 1 plus this times 1 plus this times 1, it is 6. All right. So it will be 6 again in the numerator. And now we divided by U2 prime dot product with itself. So this will be 1 square, negative 1 square, which is 1. And this will be 4, and this will be 1. So we have 4 plus 2, which is 6, right? U1 prime, that is, we said that U1 prime is V1, which is 1, 1, 1, right? U1 prime is V1. Now we are here, the next one, minus. Then we perform this U2 prime into V3. U2 prime, U2 prime, U2 prime V3, U2 prime V3. So this is V3 and this is U2 prime. So if you take dot product, this times that is negative 4, 2 times 2, 4, 0 times negative 1 is 0. So it's in total 0, but this will cancel out with that one. So the dot product here will be 0. So here already it is 0, regardless of this, so I don't really need to compute this. It is useless to know what that value is. Of course, it's transpose, it's transpose. Even if I say that it's transpose, right? Transpose to be, each time there's a transpose there, but it's fine. Dot product with itself, you understand, you take the transpose, the other one. Okay, so this is 0, so sorry. And carried by the vector itself, I don't need to know because it's already 0, so I don't need to replace it. I know that this is 0. So the final will be, okay, so this is 1, this ratio. I will just subtract 1 to all these components. So this will be 3, right? Because 4 minus 1, 3. 2 minus 1, 1. 0 minus 1, negative 1. So this is our U3 prime. Okay, now the last thing is to normalize each of the vectors. So U1 is U1 prime by the norm of U1 prime, which is, okay, U1 we know that's 1, 1, 1, so that will be 1, 1, 1 by the norm is square root of 3, right? Into 1, 1, 1. Yeah. Which is, if I want, I can rewrite this as square root of 3 by 3, square root of 3 by 3. All the components will be, okay, I write that. Square root of 3 by 3, square root of 3 by 3, square root of 3 by 3, transpose. So that's exactly the same thing it will give us. Okay, and the next one, U2 is U2 prime by its norm. So what is U2 prime? U2 prime is negative 1. Okay, so we saw that is 6. If I take the the norm square is 6, because it will be 1 plus 1, 2 plus 4, 6, square root of 6. So this is what that will give us, right? And finally, the last one, U3 prime by its norm. But U3 is given here. U3 prime is this one. So what is its norm? This is 9 plus 2. That's 11, right? Because 3 square is 9 plus 1 square plus 1 square. That's 9 plus 2 is 11. Square root of 11 here into 3, 1, negative 1. Okay, so finally, we can write our vector. Please recheck all these computations, what we have just done here. Check the computation and make sure that everything is fine, there's no error. I'm just giving you the methodology that you can check yourself, right? Yeah, to make sure that there's no error in our computation. Now, at the end of the day, this should be orthogonal. So you can check for yourself. You can check for yourself to make sure that all these 3 vectors are orthogonal. Right. If they are not, it means that there's an error. Right. Now, if I take, okay, let me check. Let me quickly check that. But before I check, let me write Q. If they are orthogonal, our Q would just be this. So this will be our Q. Q would be this basis, the last one. I didn't say it, but Q will be this F. I just take U1, U2, U3. It gives me Q. So Q should be U1, the first component, the first. That is square root of 3 by 3, square root of 3 by 3, square root of 3 by 3. And the second one is this one, which is anyway, I can still keep that. I can take this on top, right? I can write it like that, but okay. So that the first one will be square root of negative square root of 6 by 6, right? The second one will be square root of 6 by 3, right? Because of the 2 there, I will simplify, and negative square root of 6 by 6, and the last one, 3 square root of 11 by 11, square root of 11 by 11, and a negative square root of 11 by 11. So if everything is fine, this is how you write your Q. Now we will check the orthogonality to be sure that our computations are right. Now, how do I compute R from here? Because I want A to be QR, I will not stress that much to get the R, because I know that if this is orthogonal, if I multiply this by its inverse, I get R to be Q transpose into A. Because I need to multiply here by the inverse, Q inverse, this will go cancel out, and then R is Q inverse times A. But we know that Q inverse is Q transpose. So I don't need to compute the inverse of Q. I just transpose it, multiply with A, I get R. So this is how you get your R. So we are done with this part. Once you get a Q, this is how you compute R. Multiply A by Q transpose to the right, to the left, sorry, here, on the left, here. Okay, now let's quickly check that U1 and U2 are orthogonal. I will not use these factors. The factors, I will just multiply this with this one. So you see that if I take this times this plus this times that plus this times that, it will be 2 minus 1, that's 1 minus 1, 0. 0 directly. So these two are orthogonal. Now what about this and that? U2 dot product with U3. I don't take the factors, I just multiply the ints. So this will be negative 1 times 3, that's negative 3, plus 2 times 1 is 2. Finally, negative 1 times negative 1, that's plus 1. So you can see that this is 3 minus 3, 0. So these two, so the remaining is U1 and U3. U1 dot U3. So it's the same thing. Wait, there's a problem there. U1, U3, I just multiplied this, so we're adding. Ooh, there's a problem with the last one. Because this one will give me 3 plus 1 minus 1, which is 3, not 0. So there's a problem with U3. We need to check that again. U3 is wrong. U3 is wrong. So please, it's already time. Check this U3. There's a problem here. Surely we made a mistake in the computation. Check that. Make sure that we use the correct. Okay, this is V3. V3 is this one, 420. 420, yes. Now we take the dot product of U1 prime. Okay, let's quickly check that. What is U1 prime? Okay, no, U1 prime is 1, 1, 1. 1, 1, 1, that's U1 prime. With V3, and V3 is 420, 420. So what is it? Dot product is 6. 4 plus 2 is 6. We have 6 here. U1 prime, which is that, we put it there. Okay, now we divide by the dot product of U1 prime into U1 prime. Oh, this is the error. U1 prime is V1. Yes. So, no, it's 3. 1, 2, 3. Oh, no. But how did I put 6 there? This is 3, huh? Sorry. That's the error. This is 3, not 6. I don't know why I put 6 there. So this is 3. So this will be 2. So I'll be subtracting 2 instead of 1. So this is 2. So 4 minus 2 is 2. Four minus 2 is 2. 2 minus 2, 0. And 0 minus 2, negative 2. Are we together? Okay, so this is our U3 prime. 2, 0, negative 2. 2, 0, negative. Okay, that is the 3. Eh? Okay, so meaning that here, this will be square root of, this will be 4, 4, 8. Square root of 8. So this is square root of 8. And this is 2, 0, negative 2. 2, 0, negative 2. Okay, now if we check if they are orthogonal, you see, that's why it's always good to check. During a test, you should always check. If there's an error, you spot it out. So 1 and 3. Okay, that is it. You can see 1, 1, 1. So I will multiply each by 1. I will add them up. 0. That will be 2 plus 0 minus 2, 0. Ha, 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 ha. You see, you should always check. I'm giving you this example. If I didn't write that, I would have not known that there was an error. You should always check in a test, you should always check your result. So I can substitute directly what I wrote there. So this will be 2 square root, so this will be square root of 8 into 4. Because this 2 with 8 will cancel, it will be 4 here. And this entry here will be 0. And negative square root of 8 by 4. So this is Q. And that is it. We will stop here for today. I hope you enjoy all these computations and all the explanations, and you'll be able to do that on your own. Grant Schmidt, when you are asked to perform the Q-art decomposition. I hope everything was clear. We'll stop here. I will continue Friday. But it is not, it is likely, remember that we missed 2 classes. I never recorded any videos to replace those 2 classes. So it is likely that by Friday, I record 2 videos of, let's say 1 hour, or a single video of 2 hours. I will see. But it's good to record 2 videos, 1 hour. We'll see. Okay, thank you so much. Enjoy your day. God bless you and see you on.
Sir, before you go.
Yes.
When are we getting our assignment marks?
Your assignment result, not the assignment. I never return the assignment.
Huh?
The result.
Yeah, the results.
Yes. Next week you will get your result.
Oh, okay. Do we still have another assignment to do or nothing else?
No, that will depend on your overall results.
Oh.
Okay, goodbye.
Bye.